Hello everyone, my name is Bruno Marx and I'm going to present to you spatially and color consistent environment lighting estimation using deep neural networks for mixed reality. So I'm going to talk here about how to bring high quality lighting to real-time mixed reality. In this context, we have very little information about the scene and we don't have the ability to go around and measure the lighting in the scene. So I'm going to talk how to use deep learning to estimate this information instead. To talk about the context here, I'm talking here about mixed and augmented reality, where we can think as attempts to blend virtual rendered content with real-world images. Here we have two examples. The Super Mario Kart, an augmented reality racing game from Nintendo on the right, and Pokemon Go by Niantic. Both of these games use real-time rendered content blended with real-world scenarios. Here on the left we have, for example, the Pokemon and the character that's a virtual object, and the background is the real scenario. And on the right we have several elements that are virtual, like the main character, the cart, and the road and everything. And the scenario, the background scenario, here is real-world content. So in mixed reality, we make a mixture of both of these elements and to produce content. Here we have an example of lighting in the current mixed reality applications. Despite being very different environment light conditions, the three frames here show the main virtual character rendered using the same lighting. As you can see here, in all the frames, the main source of lighting seems to be above the character head, and they don't change in between the frames. So the virtual character lighting do not seem plausible, particularly in the middle frame, where the light source comes from a totally different direction. You can see on the middle frame here that the cart is under a shadowy area, and the lighting is up on the front of the character, but still we have the same lighting in the character than in the other frames. So here we have a problem with consistency of the lighting between the real world and the mixed reality world. So our main objective here is to produce a lighting estimation that allows the introduction of virtual objects in real-world scenarios, producing pleasant visuals. In these scenes here, we have relights of stock photos with virtual objects rendered with our model lighting estimation. An important aspect of our method is that it should be executed in real time. So we have to all the processing about lighting estimation should be in the rendered budget of less than 33 milliseconds per frame. So here we have several objects placed in some stock photos, and as you can see, they blended well with the environment. There is not a virtual object floating around the scene. So how our model works. Here we have an overview of our lighting estimation model. It's take as input an RGB image, and this image is acquired through a camera in the mixed reality glasses. It represents a narrow field of view of the environment. Since our input is very simple, it's even possible to use this method with a budget VR HMD, such as the Oculus Quest 2 or other headsets with built-in cameras. The RGB image is fed to a convolutional neural network that extracts features, producing the latent feature vector of our problem. We fed the resulting latent features to a spherical harmonic lighting decoder. This decoder is one part of our network output. We have two heads here. The first one is the spherical harmonic lighting, and the second one is a LUV color space mapping. So the network will estimate both of these properties, the spherical harmonic lighting and a color space mapping. The main idea is to perform a multitask between the light estimation and color space mapping to obtain a color constant lighting. If we eliminate the second head here, we have problems with some results, particularly for the lighting estimation. They appear all the same color, like grayish color, or something like this. So we introduced this LUV color space mapping here. For training our network, we need appropriate datasets. We don't have a dataset for this already available, and acquiring a real-world data for the ground truth environment lighting is a labor-intensive process. It's hard to acquire all these images for the lighting, especially because we have to capture HDR panoramas of the scene. And it's not easy task to obtain this with simple capture devices such as smartphones or cameras. So, and we need a lot of images. So acquiring this reward data is hard. Fortunately, we have an alternative here. We have some data sets with HDR panoramas already. So we can produce our data sets. Our data sets produced based on this framework that we developed called mixed reality views. A mixed reality view is a tuple of two things: the image of the environment and a ground truth lighting. The image of the environment is an egocentric view. It means that it's a view from a first-person view of the scene. It's narrow field of view. It's it's a narrow field of view that encompasses just some parts of the view, not the entire panorama. So we have this narrow field of view and a RGB low dynamic range image. We use low dynamic range image here to mimic the image of the capture device on the mixed reality headset. And on the ground truth lighting, we have a spherical harmonics representation of the lighting. So on the right side of the image, we have our framework. We start with a source HDR panorama. We perform a projection crop of this panorama to produce the image of the environment. This projection is like a simulation of the image that acquired through the camera in the headset of the user. So it needs to be tone mapped to low dynamic range, and it's also a narrow field of view of the image. Then we take the original panorama and we perform a warp operation. This warp simulates the camera moving through this HDR panorama to produce the correct spherical harmonics lighting. So with the correct spherical harmonics lighting, with the correct warped panorama, we can then project the spherical harmonics functions and obtain the ground truth spherical harmonics lighting. Please note that A, C, and D are all performed in HDR, so we don't lose information about bright spots and the shadowy portion of the original panorama. We repeat this operation several times for each panorama to produce our dataset. We have some description of the CNN architecture here. We aim to maintain as efficient as possible to achieve real-time inference time. So we use a shuffle architecture as our main feature extractor. It is fast for both training and inference. So we obtain good results with this. One of the heads of the network is our LUV decoder. So we use a Q-string architecture, just matching the downsample operations of the shuffle nets, the convent pooling layers of the feature extractor with the convolution layers. And finally, for the spherical harmonics encoder, we use just an MLP with 2 hiding layers and a hyperbolic tangent activation in the last layer. Here's some training results. We have achieved convergence at around F14 with validation loss with a mean squared error of approximately 0.004. In our test dataset, our environment maps estimation resembles the ground truth regarding the lighting distribution and the color consistency, as you can see on the right side of the slides. Here we have several examples. We try to choose some examples here that have some variety in the color. And here are some comparison with the state of the arts. We have some render images of our methods in the state of the art. In the first column, we have the ground truth lighting. The second column, we have our method estimation. If we compare with Gerons et al. In the third column, our method produces a more consistent lighting estimation regarding the color and direction, overestimating the light intensity in some cases, but producing pleasing visuals. While Gardner et al. In the fourth column estimates higher intensity environment lights and does not appear to blend naturally with the environment, at least not with some exposure compensation for the results. Here we have we analyze the spatial variant lighting, we move our model in different places across the scene, and perform the lighting estimation that should reflect the changes in the position. In the video on the left side, you can see that we move the model, the bunny model, and it reacts to the lighting in the scene. If you look for other scenes, we can have a more drastic improvements, drastic results. Here on the scene, you can see the bunny, and you have the source lighting is the window there. When you approach the window in front of the window, the object is lighting properly, differently from place when it's placed in the shadowy area of the environment. Here is another example. And finally, we have some more results here. We have some performance measurements. We fed our network with a default input resolution of 2056 by 192 pixels, increasing the resolution of the input image, resulting in increasing inference time. But we still have a real-time performance with 1080p resolution. It's important to note that increasing the resolution does not necessarily increase the accuracy of the estimation, so we recommend to use a smaller resolution input image to maintain our rendering frame budget. We also test our model in outdoor scenes. It's possible to use our model for outdoor, however, due to different natures of the environment light in those scenes, it's not possible to accurately represent the lighting. Our model produces some blending light scenarios that could be enhanced if we use some additional lighting representation along with the spherical harmonics lighting. We plan to explore this in the future.
Thank you very much.